Hello, everyone. My name is Matthew, and I'm here with Professor Chris Impey, and we are here for another live session. So, welcome. We are excited to be back. It's been a while. We've just had a chaotic month or so, and we're really just excited to be back with you today and answering your questions. As usual, the way that this works is you post your questions in the chat. I will grab the questions, do a basic curation, maybe group questions that are similar together. I try to generally go in the order that they're asked, but I skip around to try and give a variety of topics a chance to be discussed, and a variety of different question askers a chance to be heard. If you prefer to be more anonymous and send an email, feel free to do that with the link that I posted in the chat. Also, like and subscribe our channel. Subscribe to our channel and click that bell icon so that you can be alerted when we have next live session. Chris, I'll let you welcome everybody, and then we will get started with questions.
Okay, thanks. Glad to have everyone here for the live Q&A session for anyone taking our online classes or just because you found out about it and want to participate. The floor is open for your questions.
Excellent. The first question for today is I'm keen to know about the marriage of astrology and astronomy in history, and how did they separate in the present day?
It's a good question, and there is a long history there. So astrology as a pursuit, I won't call it a science because it isn't a science, dates back 5,000 years. So people have imagined, not necessarily unreasonably in pre-scientific times, that the stars and the planets had an effect on everyday life, and perhaps on the way we move through the world and our personalities. And so that's astrology, the idea that the sun and the planets and the stars at the time of your birth particularly, or throughout your life, have an effect on you. Now we know that formally the gravitational effect of these objects, except the sun of course, is minimal, negligible. And so this is not a scientific force in operation. And so there's no scientific basis for astrology. And so it's a superstition, it's a pseudoscience. But it's been held by civilizations throughout the Western world, going back to Egyptian and Babylonian time. Now around the time of the Romans, the ancient Romans, it became part of their society. And in fact, horoscopes were cast initially for the emperors and the rulers. So astrology was limited to the ruling elite, if you like. But by the end of the Roman Empire, this practice had spread down to the aristocracy and even to common people. So that was really the time at which astrology became widespread. And astrology predates astronomy because formally astronomy does not really become a scientific subject until the time of Galileo and Kepler in the 17th century. And so at that time, the two separate. So when astronomy becomes a modern science, when we have a theory of gravity that shows that the planets cannot affect us in any other way than providing something interesting to look at in the sky, astrology and astronomy part company. Astrology, as you know, continues to be part of present-day life. I read an article recently that the value in the United States of the online astrology market is over $2 billion a year. So it's a lot of money people are spending on horoscopes and readings of astrology for something that really has no predictive power at all. But some people may argue that it's a pretty harmless belief system. Scientists are a little mixed on this because it may be a harmless belief system, but it represents a lack of critical or logical thinking. And so it's probably better if people were able to recognize that astrology is not scientific.
Excellent. The next question is from Pashupati Dutta, who asks, what is the importance of Fourier transforms in astrophysics?
Fourier transforms are a sort of core method of mathematical physics, and so they have wide application in astrophysics. It's a mathematical tool at some level, so it's used in any kind of mathematical analysis where you have, for example, time series, and you want to analyze a time series. That could be a time series of observations of stars or planets or galaxies. The analysis of any time series to look for periodicities or patterns in time involves taking Fourier transforms or doing a Fourier series. But Fourier transforms have a much wider application. You can find them through all parts of astrophysics. And so it's a core foundational tool that's taught to every student of astronomy.
The next question is from Ravi Narasimhan, who asks via email, when a large secondary mirror is used as part of an adaptive optics system and flexed at hundreds of hertz, doesn't it just become a big loudspeaker? And if so, wouldn't that somehow affect the rest of the telescope?
That's a good question, an interesting question. And so the reference for the question is the fact that adaptive optics is a method of rapidly altering the surface of a mirror to compensate for changes in the atmosphere. And it's a way of taking out atmospheric seeing or turbulence in the atmosphere and sharpening up the image of a telescope to close to its diffraction limit. Now, because the primary mirrors of large telescopes are huge and have a lot of mass and inertia, this alteration of the shape is not done to the primary mirror, but it's done to the secondary mirror. So in a typical example, like the telescopes we have in Arizona, the primary mirror might be 8 meters across, and the secondary mirror will be about 1 meter across. The secondary mirror usually is a thin shell, and it's maybe only 1 millimeter across, and it's behind it are hundreds of actuators, and it's those piezoelectric actuators that are that drive the subtle change in shape of the thin shell secondary mirror. So to answer the question, yes, it's being modified, its shape is being modified at frequencies of tens or hundreds of hertz, and those are very low frequencies. Most of those are actually sub-audible. So I think it is true, and I've been there at a telescope, and you can hear a hum from the adaptive optics system. So indeed it does produce an audible sound, but that doesn't interfere with its functioning.
Excellent, thank you very much. That was a great question. The next question is from Alexa Olesen, who asks, how do we see old light with so many nearer, younger galaxies in line of sight? Do we only see old light in patches of sky where there are no other objects in the way?
That's an interesting question. And part of the answer is that the sky is not totally crowded with light. So when you look to a distant galaxy, say 5 or 10 billion light years away, sort of halfway across the observable universe, the odds that that galaxy lies behind another closer galaxy is actually very small. And so that situation essentially doesn't happen. Now, if a galaxy was perfectly aligned with a more distant galaxy, it would produce a phenomenon called gravitational lensing. So we can actually put a number on how likely this alignment is to occur, or the obscuration or the confusion of one galaxy sitting in front of another. And it's because the optical depth or the probability of lensing is about 1% or a little less. So really, it's a pretty rare phenomenon that one galaxy will sit directly in front of another. But it does happen, and these situations essentially are seen as lensing experiments where the background galaxy gets its light amplified in an effect of general relativity.
The next question is from Lawrence K, who asks, or for K Lawrence, who asks, hi, Professor, do quantum fluctuations in the vacuum of space produce virtual particles? If so, has this phenomenon ever been replicated in a lab, or is it just conceptual?
Yes, it is a standard effect of quantum physics that the vacuum of space, or the vacuum in a lab, if you create one, is not devoid of anything. It has essentially potential energy. And so in a vacuum, there's a quantum level of energy that can produce virtual particle-antiparticle pairs. And these particle-antiparticle pairs come in and out of existence in a tiny fraction of a second. Obviously, they come out of pure energy of the vacuum energy, creating a particle-antiparticle pair, and the pair will barely separate before they recombine, annihilate, and create radiation. The net effect of this is to form a sort of pressure, because the radiation amounts to a certain amount of pressure. And this pressure has actually been observed in the lab. So quantum fluctuations and virtual particle-antiparticle pairs is a real physical phenomenon.
The next question is from David McKenzie, who sent an email asking, are there any thoughts about monitoring asteroids that may be on a collision course with other planets, such as Mars? I ask because in the future we would likely or possibly have people based there.
It's a good question, and the answer is yes. I would say most of the horsepower of telescopes and computational power is clearly and understandably devoted to looking at asteroids or comets that are on potential crossing paths with the Earth's orbit or collision with the Earth. That's where most of the effort is. But those same methods and techniques can indeed be used to predict whether an inner solar system object might hit Mars in the inner solar system coming from the outer solar system. I'm aware of a couple of research groups that use their searches for near-Earth asteroids to do that kind of search as well. And the incidence rate of those potential impactors is pretty much as we might predict from theory. And we can see, of course, from the cratering history what the frequency of impacts of certain sizes are. So yes, I think it's a fair bet that as the possibility of human habitation on Mars increases and it starts to happen, probably in a decade from now, those calculations will be made with much more urgency and precision to be able to protect the colonists from a potential impact. But as on Earth, the probability of an impact is extremely low.
The next question is from one of our live participants. Alexa would like to know, what new things might we learn from the massive gamma ray burst on October 9th?
So this gamma ray burst that reached the popular media as well as scientific literature has been nicknamed the GRB, gamma ray burst, GOAT with a dash, greatest of all time. That's a sort of acronym that's used in American culture to describe sports players, essentially the greatest tennis player or baseball player of all time. Well, this is the greatest gamma ray burst of all time in terms of its energy, its energetics. And the simple answer is that we don't really know what made this particular gamma ray burst so extraordinary. It's not off scale. It's not like an order of magnitude more luminous than any other gamma ray burst yet seen. And it's fairly sure that the phenomenon itself is caused by the violent collapse of a massive star near the end of its life, leading to a sort of a cataclysm which generates huge amounts of gamma rays. So this is a particularly extreme example of a phenomenon that's very well known. There's one gamma ray burst that goes off somewhere in the universe essentially every day, and satellites pick them up.
The next question is from Faisal, who's on with us live. If the expansion of the universe continues, what happens to the microwave background? Does it turn into radio radiation in the opposite? Or if the opposite happens and the universe shrinks, does the heat of the universe increase?
Yes, the fate of the microwave background radiation, the relic radiation from the Big Bang, is intimately tied up with the expansion or contraction of space. We don't think space-time is going to contract in the future. It looks like the universe will expand forever, so we're not worried about that scenario. But in the current scenario where space-time is expanding at an ever-increasing rate, the accelerating universe caused by dark energy, then as the space increases, the microwaves that we currently see at microwave wavelengths do indeed get stretched by the expansion, and so they will indeed progress over time to become radio waves and very long wavelength radio waves. And at some point they will actually become undetectable by terrestrial technology, because we only have the ability to detect radio waves that are meter lengths or so, maybe 10 meters or so. So by the time you've gone from a millimeter to 10 meters, that's a factor of 10,000. So when the universe is expanded by that additional factor, which is billions of years from now, this relic radiation from the Big Bang will become almost undetectable.
The next question is from Hernan Reyes, who asks, recently there have been many discoveries of habitable planets, or quote, habitable planets, at varying distances from 10 to 40 light years away. Of course, what we really want to find are inhabited, not just habitable exoplanets. Aren't we a bit naive in thinking that we would be lucky enough to find such TSI, technologically savvy inhabitants during a period of time when they are able to communicate with us and be listening in our direction?
I agree that there's a huge gulf conceptually between the act of defining and detecting a habitable planet, which means a planet that could host biology, and then moving to the stage where you think there is a planet with biology, where that biology has evolved to our level of sophistication or beyond. But astronomers are in an early stage of the game of astrobiology. It's a young field, barely 50 years old. Exoplanets have only been known for about 30 years. So that's where the game is. The game is currently the ability to detect habitable planets. And even their habitability, of course, is a very particular definition based on the possibility for liquid water on the surface of a terrestrial type planet with an atmosphere. And we know that there are habitable regions of the Earth that are immune or do not depend on photosynthesis or the sun's radiation. So that's certainly a myopic view of habitability, but it's the best you can do. We do not have the technology to detect life deep in an ocean or within rock on a terrestrial planet, and we may not have that for decades. So essentially astronomers do what they can. And as for the more advanced forms of life, that's a completely different scientific field, of course, called SETI, the Search for Extraterrestrial Intelligence, that uses radio and optical techniques.
The next question is from David Gold, who also has an expansion and light-related question similar to the earlier one. How does the ultraviolet light from the beginning of galaxies become infrared light by the time it reaches telescopes?
So from the early phases of the universe, we've now seen galaxies that are at redshifts of 10, which means their light has been stretched by formally by 1 plus the redshift, so a factor of 10 or 11 since that light was emitted. So that means ultraviolet light, say light that might have been at 200 nanometers wavelength when it was emitted from very hot blue stars in a young galaxy at a high redshift in the distant universe, that is stretched by, as it passes through the expanding universe for 13 billion years, that is stretched by an order of magnitude. So a 200 nanometer ultraviolet wave from the galaxy turns into a 2000 nanometer, which is 2 microns, that's near infrared wave in the nearby or in the current universe as we detect it. And that's exactly what James Webb was built to detect. James Webb could not detect the ultraviolet radiation or even the blue parts of the visible spectrum. It's really designed mostly to detect reddish visible light and near infrared and mid infrared light.
The next question is from Julian R., and we can talk about this sort of broadly. Julian would like to know, are there any prerequisites for attending classes? And so we can take a second to plug our online classes. So the ones that we mentioned at the beginning of all of these live sessions are offered on Coursera and Udemy. And Chris, you can talk about that for a moment.
Sure. So we offer 3, soon to be 4 MOOCs, Massive Open Online Classes. Our first one was on Udemy dating back to 2013. And after that we had an astronomy course, Exploring Space and Time, on Coursera from about a year after that. And then an astrobiology course, I think, that launched in 2019. And we have a brand new one that will be out very soon on the history and philosophy of astronomy, also for Coursera. All 4 of those courses, 1 on Udemy and 3 on Coursera, are available free. They're open to anyone, they're free. I think there are restrictions on very young people registering. Perhaps under 16 is not allowed by Coursera. I'm not entirely sure of their rule, but really they're open for anyone. They're free. However, if you choose to avail yourself of a completion certificate, so you want some recognition of the fact that you did all the assignments and evaluations and did well in them and looked at all the content, you can get a completion certificate, and for that you would pay $100. $30 of that goes to Coursera, and $70 of that comes to the university, and a little bit of that comes back to our department and helps us create these courses.
Excellent. The next question is from one of our live participants. Ishita asks, what is a wormhole?
Wormhole is a hypothetical rupture in space-time that connects to another part of the universe and is a portal essentially for energy. And for matter. It could be it could even be a physical pathway where physical objects can pass from one part of space-time to another. Now, wormholes are allowed in general relativity because general relativity is based on curved space-time. So a wormhole is just a very extreme form of curved space-time where the topology or the geometry of space-time is complicated enough to allow interconnected regions, and that's really what a wormhole is. So this is all possible theoretically and hypothetically. General relativity allows it, but there is no evidence at all right now that wormholes exist in our universe. And that's because our universe has a mostly simple geometry. Space-time is essentially flat on large scales, and the only places where we see much deviation from flat space-time are very, very close to extremely compact objects, neutron stars and black holes. But even in those situations, we've seen no evidence for wormholes.
The next question is from one of our live participants again. The 800 millimeter telescope project asks, can you give us an update on the giant Magellan telescopes? Are the mirrors now complete?
So we have 5 mirrors complete, and the 6th one on its way, and the 7th one planned. That's the last. And the schedule for the Magellan is, of course, that full functioning of the telescope, 22.5 meter effective aperture based on 7 8.4 meter mirrors held all together in a sort of shape of a flower, petals of a flower. That requires 7 mirrors, but if you just take the central element, the central mirror, and 3 of the petals, you can use a 4 mirror first light instrument. And so it's planned that Magellan, the giant Magellan, will start with 4 mirrors, and those all exist. They've all been polished, and the building is under construction in Chile, and then a few years later you go up to 7 mirrors and the full capability. The timeline is stretched out a little. COVID has made a lot of problems for big capital projects, not just in astronomy but across science. It's a widespread problem in science. So things did not exactly grind to a halt by COVID, but they actually slowed down a lot, and that also of course increased the cost of the projects. So the Giant Magellan Telescope his budget's gone up, and we actually need more money to complete it. And the schedule for the first light is currently, I think, 2029 for the first light, and that would be the 4 mirror system, with the 7 mirror system coming maybe a year or 18 months after that.
The next question is from Ayla, who would like to know, hello, Professor, can you talk about how magnetic fields may affect spacecraft?
Certainly. Magnetic fields are a significant issue in space. In the depths of interstellar space, there's no strong magnetic field, and so it's nothing that anyone would worry about. However, the sun obviously has a strong magnetic field, so any object, any spacecraft traveling close to the sun would be affected by that. Earth has a strong magnetic field, and Jupiter also has a strong magnetic field. Smaller planets don't tend to have liquid metal cores, so they don't have strong magnetic fields. Mars, magnetic field very weak. Mercury, none at all. What the effect on a spacecraft is that traveling through a metal object, traveling through a magnetic field, will induce an electrical current. This is just a space version of an experiment that Michael Faraday conducted in the late 18th century at the foundation of electromagnetism. So you're generating electrical currents, you're inducing electrical currents by traveling through a magnetic field in a spacecraft, and that can create a problem because the spacecraft has a lot of delicate circuitries, computers, guidance systems, and so on. So basically, aircraft designers or spacecraft designers do it too, have to design for this. Essentially, you need to make an external shell of the object, a Faraday cage, that immunizes the interior circuitry from interference by that magnetic field and the electrical currents that it will induce.
The next question is from a live participant. So Drishti is a high school student and would like to know if you can use simple language to discuss the difference between dark matter and dark energy.
Sure. So the simplest way to talk about these two things is to say that we don't physically understand either of them. So they are mysteries and unsolved problems in astrophysics, but we have evidence to think that each of them exists. In the case of dark matter, we see galaxies rotate faster than they should based on the visible matter and normal gravity law. We see, and we also see large clusters of galaxies, the galaxies in the cluster moving faster than they should based on the visible matter. We also see light deviating as it travels through intergalactic space induced by dark matter that's not visible. So on many different large scales in the universe, we see evidence for some form of matter that's not visible or doesn't emit or interact with light. And it exceeds the normal matter by a factor of 5 or 6 in mass. Dark energy, we're in less sure footing. We simply don't know what it is. All we know is that the universe's expansion is accelerating. The expansion, galaxies moving away from each other, is getting faster and faster. And that does not have a normal explanation in the conventional cosmology. And so we infer the presence of something we call dark energy that exerts a pressure that causes space-time to expand at a faster and faster rate and the galaxies to move away from each other faster and faster. But it's important to know that while we think both of these phenomena exist, we don't physically understand them at a deep level.
The next question is from Pramod, who asks, we always see green-faced aliens like the one behind you. Can you discuss how on the cellular level structures as well as various organs might be different or similar?
Right. I mean, it's an interesting point that it is indeed true that we see green aliens in the popular culture. You go science fiction and movies and films going back over 50 years, including the alien that sits behind me. And it has to be assumed, I presume, that green pigmentation is caused by chlorophyll, as it would be in plants. It's not clear why an alien species would have chlorophyll in it, so maybe it's some other chemical. But the simple answer to the question is alien physiology is completely unknown to us because we haven't found life on any other planet. And we haven't found any form of life, and that probably will first be microbial life. It won't be large creatures like aliens or plants or animals. So we are very far from understanding what the complexities of alien physiology would be and how different it might be from our physiology. But it's certainly true that life forms always use energy, and life forms may use and filter and reflect energy that they get in different ways. And so their colors may be quite different from each other, and they may not all have the range of pigmentations or colors that humans have, or remembering that plants and animals in the animal kingdom on Earth have an enormous range of colors.
So the next question is from Yang, who asks, do you believe nuclear biochemistry can make the modern derivative of astrology something into astrobiology, such as evolution and biochemical abundance relative to the cosmological scale? So I guess I'm not entirely sure I
don't get the connection to astrology in that question. So say it again.
I guess do you believe nuclear biochemistry can make the modern derivative of astrology into something astrobiological? Yang, why don't you ask the question again, maybe give us some more details, and we'd be happy to address it. But I'm having trouble kind of deciphering what you mean by that. So We'll jump to the question from Lysos. Is dark energy a thing, or just a name that we give to whatever mechanism is causing the accelerating expansion of the universe?
I think it's the latter at this point. It's just a name we give to something causing the acceleration of the universe, because that's the result from 1995 that we are confident is a real result. It led to the award of a Nobel Prize in physics some years later. So that result, the accelerating expansion of the universe, is pretty firmly established observationally. The imputation of what is causing that accelerating expansion is completely unclear. There have been hundreds, actually now thousands, of theoretical papers written about dark energy and what it might be, and very little guidance from observation. So we are still sort of in the Wild West when it comes to understanding dark energy.
Ayush would like to know, why is it that mass is the key factor in deciding the future of a star, whether it will be a black hole or not?
So mass is the driving factor in the evolution of a star, to the level that it was Arthur Eddington who came up with the theory of stellar evolution in the 1930s, working at the University of Cambridge in England. He said, if you tell me the mass of a star, I will tell you its full life story. So it's pretty simple. And the reason for it is that the mass of a star dictates the amount of gravitation it has, the gravity force. And given that it's composed of hot gas or plasma, the gravitational force will then determine the temperature inside the star. And that temperature will determine what kind of nuclear reactions can occur. And as those nuclear reactions evolve or change over time and nuclear fuels are exhausted, the gravity doesn't change. So the mass of the star continues to change to drive the pressure inside, the temperature inside, and what nuclear fuels can be created by fusion. And so mass is all the way through driving the evolution of a star. Now it's complicated by the fact that at some stages of a star's life, near the end of its life, as with the Sun, 5 billion years from now, mass gets ejected in violent episodes, just normal mass loss in red giants or violent ejection in a nova. And that loss of mass, of course, changes the gravitational force calculation, but it's still the case that the mass retained by the star continues to drive its evolution right the way to its fate as either a white dwarf, a neutron star, or a black hole.
The next question is sort of a definition question. One of our viewers is on like dictionary.com, and the word for the day was evection, which was defined as a periodic irregularity in the moon's motion caused by the attraction of the sun. And Hamid would like to know, can you explain why, if the sun is pulling on the moon at a constant rate, that for some reason the motion might be irregular?
These are subtle irregularities. So indeed the sun is pulling with a steady force on the moon, but for example the Earth-Moon-Sun system has a number of variations. The Earth's orbit is elliptical, the moon's orbit of the Earth is elliptical, it's inclined relative to the plane of the Earth's orbit of the sun, and these complications are quite significant because they mean that because of the ellipticity of the orbits, moon around the Earth, Earth around the sun, the speed of the orbits varies, and that means the distance varying will create a different gravitational force. Now, it's not completely irregular. There are subtle patterns in these variations, but it amounts to a change from the sort of steady gravitational pull.
So as a follow-up to the previous question about black holes, one of our students is just incredulous. I mean, how is it that mass collapses into a black hole very dense? Is it really just gravity that's causing a black hole to collapse that small and that dense?
It is indeed gravity. So this is the inexorable and inevitable force of gravity. Gravity is generally counteracted in a normal star by pressure caused by radiation released from nuclear reactions. So the sun's size and mass doesn't change for close to 10 billion years because the gravity is in balance with energy produced by the fusion of hydrogen to helium. As soon as that balance is broken, however, and especially as nuclear fuels are exhausted, then gravity is always there and gravity will start to win. And so the black hole represents essentially the final victory of gravity after all nuclear fuels have been exhausted. And in a massive enough star, it's not true for all stars, this would be a star that started its life as 7 or 10 times the mass of the sun. When all the nuclear fuels have been exhausted, the gravity is strong enough to force the object into a state whose density is such that the escape velocity is the speed of light. And at that point, it becomes the definition of a black hole.
Wendy Traver sent an email asking, in light of the James Webb telescope's most recent imaging of the moon Triton, what are your thoughts that it might be an escaped Kuiper Belt object?
It's an interesting hypothesis, and it's certainly plausible. The moons in the outer solar system are interesting. It's obviously been known for a while that the number of moons increases as you go down to smaller and smaller moons. The census of moons around Jupiter and Saturn is 60 or 70 each, and several dozen for Uranus and Neptune. Now, the large moons are an interesting category because you have enough orbital information to look at their nature of their orbits and decide what the odds are that moon was born there and born in orbit around the planet or was actually captured. And so some of that depends on the inclination of the orbit, the ellipticity of the orbit, and also the mass ratio of the moon to the planet. Because you can only naturally make moons from the debris disk left around a planet that are quite small relative to the planet. So the largest moons could quite plausibly have been captured, and I think the case has been made for Triton that that was the case. It's not convincing yet. I think there's counter arguments, but it's certainly an interesting hypothesis.
The next question is from Stephen Smith, who's on with us live. With Voyager 1 and 2 traveling almost to the limits of our communication with them, are there any plans to send other spacecraft on similar extragalactic missions?
Well, they're extrasolar missions, so we haven't had any spacecraft leave the galaxy yet. That would be a very tall order, although I suppose eventually it could happen millions and millions of years from now. So at the moment, the Voyagers were the first pair. We have the Pioneer spacecraft 10 and 11 that have left, and then most recently New Horizons, the one that took that fleeting image of Pluto as it whipped by heading towards the edge of the solar system. So we now have 5 spacecraft that are heading into interstellar space. At the moment, there's no current mission that's heading to leave the solar system, but that actually is going to change, and that's partly because the outer solar system has had a negligible amount of activity recently. But people are starting to get more interested in the giant planets. New Horizons spurred some of this interest by showing that Pluto, which is formerly a dwarf planet, was much more exciting and perhaps even astrobiologically interesting than we ever thought. So there are certainly missions that are planned in the next couple of decades to look at the outer solar system, which would have the speed and the capability to leave the solar system. But at the moment, it's just the 5 satellites that we sent decades ago.
Excellent. The next question is from an email. Is the universe becoming more stable in time as we move out from the Big Bang?
It's not clear if the universe is becoming more or less stable with time. So stable is an interesting word because it implies that it's reached some sort of equilibrium. And in a sense, the universe has reached an equilibrium because it's an equilibrium where there's no countervailing force that will change the nature of the expansion. Back when it was possible there was enough dark matter, and we didn't know about dark energy, that the universe might recollapse, you could consider that an unstable universe because it allows the possibility of an oscillating universe. That was an idea that was quite prominent in the 1950s and the 60s. But we don't really have that model on the table anymore. And so in a sense, the universe is quite stable because it has one trajectory as far as we know, and that's just ever-increasing expansion.
The next question is from Mr. P. And we also have another related question that's generally about string theory. So Mr. P is interested in brain cosmology. So first, can you start by talking about what you think about what's the current state of string theory in terms of the scientific acceptance of this idea?
Sure. I may have to give short answers here because this is a big topic. So you could have a whole hour-long lecture on this, clearly. So string theory is in a holding pattern, is the best way I'd put it. String theory was an ambitious attempt to go beyond the standard model of particle physics and hypothesize the deepest level of structure of matter consists of tiny one-dimensional strings which interact with each other and generate the properties we normally attribute to particles. And those strings are only manifested or visible on incredibly small scales, much smaller than a proton, and at incredibly high energies, much higher than we can achieve with any accelerator. And because of those reasons, it's very hard to test string theory. So string theory is mathematically quite mature, but experimentally extremely immature. That's the simplest way to summarize it, in the sense that it's very hard to make testable predictions from the theory, and so far no predictions have been tested, and so we really don't know if string theory applies to the universe we live in.
And then the follow-up question to that is from Mr. P. In brain cosmology, since, I mean, it's hypothetical, but hypothetically, if one were to create a theoretical or actual starship, how would space behave when the crew of the starship, they say here, make the transition from the brain to the bulk, but I guess the question is, how would they interact with this membrane, this brain?
Right. So brain cosmology, just to explain it briefly, is based on string theory, this fundamental new view of matter as tiny one-dimensional strings. And the formal theories for string theory that work mathematically almost all involve multidimensional space-time, 10 or 11 dimensions of space-time. And so it's assumed that the 3 dimensions of space and 1 of time that we see are visible macroscopic representations of a larger manifold of space-times that are invisibly small. And so that's where brains come in. Brain is a membrane. It's just a higher order dimension that's invisible to us because we need very high energy to access it. So the idea, or the hypothetical idea, of traveling between the brains or from the brain to the large-scale universe we live in, 3 dimensions of space and 1 of time, is doubly hypothetical. It's not clear that you could ever travel between dimensions in this way, and more importantly, it's not clear if those 9, 10, or 11 dimensional space-times even exist, and that our universe is a brain cosmology. So brain cosmology is highly speculative, is the simplest way to put it.
Pramod asks, if math and physics would be a language to communicate with aliens, how do we communicate things like "don't harm us" or other more complicated or abstract sentiments?
That's a great question, and the people who do SETI, the Search for Extraterrestrial Intelligence, or METI, the act of messaging extraterrestrial intelligence, worry about this all the time. So it's true that the simplest thing you can do to an alien civilization of unknown function and form is to convey the fact that you understand the laws of physics, how the universe works, and the abstract concepts of mathematics. And so people have put a fair amount of effort into thinking out ways to convey that we understand that and coding it into a message. But to do those higher order communications, you're immediately in trouble because you need a language. The language of mathematics is a language. The language of physics is a mathematical language, essentially. But the language of culture and the language of values and the language of ethics is a totally different thing. It requires a linguistic basis. It requires comprehension. It requires a common experience, essentially, of the alien and the human who's trying to communicate with. And most people think a priori that's extremely unlikely to be possible. So it's a real stretch to imagine that we could communicate with an alien advanced species of unknown function and form, given how difficult language and culture are. Put it this way, we share the planet with creatures with whom we share 99% of our DNA, chimps, and we can't talk to them. And so how hard would it be to communicate with an alien of unknown function and form that didn't even have DNA?
The next question is from Drishti, who's on with us live. What really causes time dilation?
So time dilation is an effect of general relativity. It was one of the predictions of the theory right from the first time it was published in 1916. People worked through the consequences soon after that. And it's the prediction that time, which in Newton's gravity theory is an immutable thing, time is imperturbable and flows uniformly and constantly through space and through time, never varies. That's the simple Newton theory of gravity. Time is just a constant. In Einstein's theory, space and time are coupled, and they're formally coupled through the equations of general relativity. And that means that when space is bent, or space distorted by mass and energy, that time is distorted as well, because the space and the time are coupled mathematically and physically. And how that manifests is that stronger gravity, time, clocks, anything you use to measure time, a physical clock, an atomic clock, a human experience of time, will be distorted by gravity to run slower when the gravity is stronger. And the extreme version of this is, of course, at a black hole, where the gravity is so strong that time essentially freezes. Now that's never been tested, but the time dilation effect has been tested. In fact, in the 1950s, physics experiments using decaying particles in different parts of the Earth's gravitational field, high and low in a tall building, for example, a lab, it's been shown that the time dilation is a real effect. So general relativity in this aspect has been verified.
The next question is from a live participant. Do you have any idea how Copernicus was able to make the leap to the conclusion that the Earth rotates and the sun is the center of our solar system, even though he was a religious monk and not a mathematician or an astronomer?
Yes, it is a great leap, and it's a revolution. His book was called On the Revolutions in Latin, and what he did was revolutionary in our modern sense of the world, meaning violent political and social upheaval. It was a violent change of ideas to the faith, to the culture, to the Catholic Church, to even everyday people who are used to the Earth being the center of the universe. How did he make that leap? Was with great difficulty. He was an excellent mathematician, as well as being a cleric in the Catholic Church, so he's a religious man. But he was driven and guided by science, so he was a scientist. And by the time he'd been looking at this for 20 years, motivated by the fact that it was very hard to predict the positions of the planets, and the retrograde motion of Mars in particular was a puzzle in the geocentric model, he realized that it was more elegant, more economical, more efficient to have the sun at the center and the planets of the orbits all going around the sun, including the Earth. And so it was almost for aesthetic principles that he went to the sun-centered system, because the verification of it actually took quite a long time after his death. It was a momentous move, we know, because he labored on this very hard, and he was hesitant to publish it. In fact, he only published it on his deathbed, and he got a friend called Redicus to write a kind of an apologetic introduction to the book on the revolutions, which essentially was trying to tell people, especially the officials of the church, don't take this too seriously, it's just a mathematical idea.
The next question is from Anjali, who would like to know, which light travels fastest in space?
All forms of light travel at the same speed. So this was a fundamental result of the electromagnetic theory of James Clerk Maxwell. So Maxwell in the 1860s and 1870s developed the electromagnetic theory. And the electromagnetic theory posits that light is a coupled electric and magnetic oscillation that travels in a vacuum at 300,000 kilometers per second. And in his theory, the nature of that oscillation traveling through space or a vacuum doesn't depend on the wavelength or the energy. And so light of all colors and wavelengths and frequencies travels at the same speed, as do radio waves, X-rays, gamma rays, etc.
The next question is from Aisha. I recently read a book, The World According to Physics by Jim Al-Khalili. There was a chapter on matter and mass, and there's a concept that I just can't understand, and I'm hoping that you can explain. The quote is, however, even mass does not always remain constant. The faster a body moves, the more its mass increases. This is not something you would be taught at school, and Isaac Newton would have found it astonishing because it is yet another consequence of the nature of space-time, as elucidated by Einstein's special theory of relativity. So can you talk about that comment, the faster a body moves, the more its mass increases?
Right. In Newtonian physics, mass is immutable. Mass does not change based on the motion of an object. And Newtonian physics is still correct in the everyday world, but Newtonian physics deals with objects that are moving at what we might call normal, slow speeds, that are speeds slow compared to the speed of light. All terrestrial objects, even the fastest spacecraft, are moving at tiny, tiny fractions of a percent of the speed of light. As you move towards the speed of light, or relativistic velocities in Einstein's special theory of relativity, his equation E equals mc squared comes into play. And what it means is that mass is interchangeable with energy. And so in the theory, as an object is increased in its speed, because the speed of light is an absolute limit, eventually the energy you put into trying to increase its speed actually just goes into increasing its mass. So its inertial mass, its resistance to motion, is changing because you're putting energy into it to make it go faster. Instead of making it go faster, it increases the mass. And so an object could never reach the speed of light because however much you try and accelerate it, you're just making it heavier and heavier. And we see this because we see no object that's ever able to go faster than the speed of light. At CERN, protons are accelerated to 99.999% of the speed of light, and their mass increases by an order of magnitude compared to what they would be stationary in the lab, but they can never exceed the speed of light. So Einstein's special theory of relativity and the suppleness of mass, depending on its motion, has been demonstrated amply. I mean, it's a foundational part of physics now, and it's seen experimentally all the time.
The next question is from Alexa. With so many Earth and space telescopes available to us, including ones that see billions of years into the past, how is it that Oumuamua went out of our view so quickly?
Well, these telescopes are indeed very powerful, but the problem with Oumuamua, or any object like that, any transient object that comes in and out of the solar system, is that it's a very small object. Anything that's about the size of a comet or a small asteroid, by which we're talking about 5 or 10 kilometers. When that object is near the outer solar system, at a distance of Jupiter or Saturn, so a few billion miles, the reflected light that object has, it doesn't emit its own light, so all we can do is get the reflected light from the sun. So the sun's radiation has to travel a couple of billion miles. It reflects off a tiny object, and some very small fraction of that reflected light comes back to the Earth. So these objects become incredibly faint, and essentially they become fainter than any galaxy. And so it seems illogical that it would be harder to detect Oumuamua as it leaves the solar system than a galaxy 13 billion light years away. But the galaxy 13 billion light years away consists of hundreds of billions of stars. And so in the aggregate, its light is a lot more than that feeble reflected light from a very small rock very far from the Earth.
The next question is from Christina V, who sent an email. Do all the clouds of gas in the universe eventually undergo a gravitational collapse? Do they all eventually get enough of a little disturbance to start the gravitational collapse, or do some of them just stay dormant forever?
It's a good question, and really the answer is yes, some of them can never collapse. The collapse is not an inevitability. Essentially, collapse involves it has to go out of equilibrium. So you can have a gas cloud, for example, this is a typical phenomenon, which is very big and diffuse and has a modest amount of rotation, just a small amount of rotation. And that angular momentum can be sufficient to keep that gas cloud large, and so it will never collapse for that reason. Or you can have a gas cloud that has almost no rotation at all, that's just diffuse enough that it never tips over into the state of gravitational collapse. So that's possible too. And so there definitely are gas clouds that never collapse. On a larger scale still, the universe is expanding. And so gas clouds within galaxies are immune from the cosmic expansion, but on the very large scales between galaxies, the gas is getting more and more diffuse. And so the likelihood of gas on very large scales collapsing goes down as the universe gets older.
The next question is from a live participant, Albie. John Albie asks, could dark matter be present on Earth, and is dark energy only present at the edge of the universe?
Yes, dark matter could, and in fact should be present on the Earth because dark matter permeates space. We believe it's a ubiquitous ingredient of the universe. It interacts very weakly with radiation, if at all, but it exerts gravity. And so there should be dark matter within the solar system and around the Earth. And in fact, many dark matter experiments are not based on using telescopes, but they're based on using experiments typically deep in mines to shield from cosmic rays and other confusing signals. And they use volumes of extremely pure gas or liquid to look for direct collisions of the dark matter particles that are ubiquitous and all around us with atoms in the gas or liquid. And then that mechanical energy of a collision is what's detected. So that's a standard method of dark matter detection in laboratories deep underground. And that may be the way dark matter is actually detected, but it is on Earth. Dark energy is also pervasive, and it's not just at the edge of the universe. Dark energy is supposedly responsible for the accelerating expansion of space, and every part of space-time is accelerating at the same rate as far as we can measure. Dark energy strength does not seem to vary with time or with direction in the sky. And so dark matter is pervasive and present everywhere in the universe.
The next question is from Karen. As since two PIs, principal investigators of Webb's Space Telescope's instruments, are at your university and therefore get a large share of the time allotted for research, can you summarize what they're focusing on?
Sure. So we have two investigators that were leads in two of the James Webb instruments, the mid-infrared camera and the near-infrared spectrograph and camera. That's Marcia Ricci and George Ricci. They're married. They've been married for decades. They're two of the senior members of our department. They're both Regents professors, the highest accolade of the university, and they're, of course, very esteemed in the astronomical community. And each of them and their teams, not just going to them personally, and the teams are actually, in both cases, have well over 100 people involved. The instrument teams for James Webb, as a reward for all the work they did for the community in building these instruments, which will be used by everyone in the community, they do get privileged time, and especially in the first cycle of the telescope, hundreds of hours of observation. Those lists, the target lists that they're observing, have been made public, and they're not just doing one thing. Of course, each of those teams are doing a variety of things. They're looking at distant galaxies, they're looking at exoplanets, they're looking at star formation regions, they're looking at novae and supernovae, they're looking at young stars directly in the act of formation. So there's a list of astronomical topics that's very wide ranging that each of those instrument teams is going to address with their time. And that time is theirs indeed for a certain amount of, for a certain period, but after 12 months after they get the last of their data, it starts to go public. And so they can't just sit on the data and take their time to reduce, analyze, and publish it, because eventually other people will be able to work with that data too.
Sorry, a little glitch with my mouse. Van Robinson asks, what is different in the construction of the JWST that allows it to observe in infrared?
It's mostly the instrument, but it's also the mirror. So the mirror, you need a mirror coating that it's a very efficient in the infrared, and the James Webb Space Telescope has gold coatings on its mirrors, and that's a highly reflective surface for longer waves of light. Whereas you can use aluminum in the optical, and that's most efficient for shorter wavelengths. But it's the instruments really where the detection matters. And those instruments are different. They're sort of roughly equivalent to CCDs, charge coupled devices that we all have in our cameras and cell phones. But they're somewhat different because they have to work at longer wavelengths. So they're actually looking at heat radiation, essentially, in the infrared. And so electronically, in terms of the detectors and the semiconductors used, they work differently. But in the end, they're just converting light, radiation energy, or heat, if you like, because it's infrared, into an electrical signal that then can be read out and digitized and turned into an image that you could see.
All right, and this will be our final question for today. Lamborghinius, which I think is a great handle, by the way, would like to know, why doesn't NASA look for alien life with the JWST?
Well, NASA is going to look for alien life, but actually NASA doesn't use the James Webb Space Telescope. NASA is obviously a caretaker of it, but NASA doesn't apply. NASA scientists can apply for time on it, and some do, and some have time, but NASA doesn't actually get to do the research. NASA is the, like I said, is the caretaker, if you like. But the investigators that are using James Webb are trying to look for alien life, but they're not able to look for advanced forms of life. The experiments that they can do involve looking at exoplanets, probably super Earths, and trying to look at their feeble reflected light from an atmosphere of a super Earth and see what ingredients there are in a spectrum. And they're looking for biomarkers. They're looking for things like oxygen, ozone, methane, and water vapor, of course, because all of those are signposts for life on the Earth, and we assume they would be elsewhere. And so that's the experiment of detecting biomarkers that James Webb is doing. It's also going to be done by these very large telescopes that we're building on the ground, 3 of them coming in the next decade that are all 30 meters or so in diameter. Very competitive field. And we really hope that eventually microbial life will be detected, perhaps this decade. Thanks again. That's a lot of good questions, big range, cosmology to comets, and everything in between. So thanks for participation. Thanks to Matthew for facilitating, and he can say when the next session is because I can't remember at the moment.
Of course, the next session will be next Thursday. Next 2 weeks on Thursday the 17th. So right. 2 weeks from tomorrow on Thursday the 17th at this time. And thank you all for joining us. Again, make sure you subscribe and click the bell icon to receive updates about the next live sessions. The next live session will be on Twitch, and we will send out the link for that on our Teach Astronomy Twitch channel. We are looking forward to seeing you all then, and we hope you have a great rest of your week. Take care, everyone.